This is the posted Excel sheet with the generic data for Lab 10.1 stress and strain. And I'm just going to use the data that I took in the video that I posted on YouTube. So the original length for my rubber band is 90 millimeters, for the width 4 millimeters, for the thickness 1.5 millimeters, and then notice that back here the volume is automatically calculated to 540 cubic millimeters. Okay, then here I would put in the mass data. Of course, if you have 100, 200, 300, you can just leave them like that. I'm going to take these data out, these 3 rows, but I'll leave the first row because the first row has already all the calculations in it. So it's just a matter of copying, and I'll show you that in a few moments how to do that. Here are the length data that I measured. So for 100 grams that would be 100 millimeters, then 120 millimeters for 200, 160 millimeters for 300, and 208 millimeters for the 400 grams. So those are 4 data points that I did in my example. Okay, so now I'm going to grab here the column for the weight. I'm going to grab the lower right hand corner, you see that little square there, and pull it down for the first 4 data, and it automatically calculates the weight, and it makes sense that at 400 grams multiply by 10 or 9.8 the gravity and convert the units by dividing by thousands. 400 grams comes out to almost 4 newtons. So that's what's happening there. On this one here, this is the change of length. Here is what it calculates, is subtract the 90 millimeters from for the original length. So at the end, 208 minus 90 is going to be 118. There it is. The cross-sectional area, what it does here is it divides the original volume by the total length, and what that does is it gives us the cross-sectional area. Of course, the rubber band expands, and so its cross-sectional area is going to become thinner, and of course eventually it's going to rip. That's why the cross-sectional area is just going to get smaller and smaller. This assumes that the total volume of the rubber itself is going to stay constant, and you divide by the length and you get the cross-sectional area. That's why you don't have to measure the width and the thickness anymore. You only do that once in the beginning to get the original volume. Okay, the strain divides the change of length by the original length, and this could be interpreted as a percentage. So here the length has increased by 11%, here the length has increased by 131%, and you see that the rubber band gets pretty long. The stress divides the weight that you put on by the cross-sectional area, and of course the weight increases and the cross-sectional area decreases, so you divide a larger and larger number by a smaller and smaller number, so that number really does become really large, and you could perhaps compare 1.5 million pascals for the stress with atmospheric pressure, because they have the same units, and it would be 15 atmospheres if you could compare really stress with pressure. The Young's modulus here should be a constant for normal materials, but rubber is not a normal material because it behaves differently. A normal material like steel would just expand nicely linearly, while here rubber is going to expand, and you will see at first quite a bit, and you will see that in the experiment that later on, the more weight you put on, it hardly expands anymore. So the curve that you're then going to get is graphed here automatically. The more data you put in, the more is going to be graphed, and eventually it's not going to look linear like this here, but it's going to increase like this here, and that's what I just mentioned a moment ago. As you go further out to the right, it doesn't increase anymore the more, even though you put more weight on, but you will see that when you have more data. And that's how you evaluate the data from this lab.